All right, good morning or afternoon, everybody. So we are going to move on from ff prime and start looking at another relationship. So at this point in time, we have connected the concepts of the f function to the f prime function. And we've realized that there's a relationship between those such that as the f function increases, we can identify increasing and decreasing segments of f based on the sign that f prime has. Another thing that we get interested in, though, is a concept called concavity. And what concavity is specifically talking about is the idea of how the graph is curved. And there's two types of concavity, and should be absolutely nothing that you're used to. You started dealing with this back when you dealt with quadratics and you dealt with, does the quadratic open up or down? And when a curve is open in a downward facing direction, we say that this curve is concave down. And when the curve is moving in an upward bell-shaped curve like that, we say that it is concave up. And so basically the idea is that if we think about each one of these little curved sections as little quadratics, and hey, this is a quadratic that would open down, we'd say, hey, that's concave down. A quadratic that opens up, it's concave up. And in between that, at some point in time, there's a spot where the concave down function and the concave up function, we change from concave down to concave up, and we call that point an inflection point. In fact, let's go ahead and let's talk about that real quick. So actually, this is all definition, so I guess I didn't want to talk about that. I apologize. Got ahead of myself. So we've got that thing going on. And concavity gets to be a really important concept because the idea here is that it tells us actually how our rate of change is changing. And we'll talk about that in just a minute here. So what I want to do is I want to pull this over here. And I want to look at this section. So what we notice first is that in this section, in fact, let me put one right here on that spot, and then I will put one right here on this spot. So I'm going to look at the region right here between 0 and pi over 2. Between 0 and pi over 2, we can tell that the function is increasing for f of x. And if we look at f prime of x by cosine of x, we know that that is a increasing function because f prime is, we know that f is an increasing function because f prime is positive. But more interestingly, you'll notice that my function is on a concave down section. And one of the things we get interested in, we ask is, well, hey, what is the concavity here? How can we tell based off of my relationships between f and f prime? So if I'm looking at this region and we look at the slopes, if I'm looking at the slope here, you'll notice this is kind of steep, but as we keep increasing along the x-axis, you'll notice that eventually the tangent lines start to become less and less steep. And in fact, we can actually identify that if I remember that the tangent line slopes here really are my f prime function. If I look at that, we can quite obviously see that if f prime starts off positive, our f prime is moving lower and lower, which means that my curve is becoming less and less and less and less steep. It's still increasing because f prime is positive, but it's getting less and less steep until suddenly, bam, here at pi over 2, we have a zero slope. And we can see that here at pi over 2, we have a zero slope. That suddenly we're got this nice horizontal tangent line. Well, that decreasing section is actually, because actually if we move on a little bit further and we look between the next section, you'll notice that this is still concave down. And if I look here between pi over 2 and pi, you'll notice that this is now a negative slope, but it's getting steeper and steeper and steeper and steeper. Or you could even say the slope is decreasing, but it's decreasing to further and further and larger and larger and larger negatives. You'll see that the function is still decreasing. That's because on a concave down graph, when a graph is concave down, we say that in that region the slope is decreasing. So when our f prime is decreasing, we can see that our f is concave down. Likewise, whoops, grabbed the wrong thing. Likewise, if I grab this and I look at the concave up section, you'll notice that on f prime between pi and 2 pi, that this function is decreasing negative slope, but then you can see that our slope is increasing. And during this entire region where my slope increases, you can see that my function, f of x, is concave up. Now, this is all well and good, but sometimes if I have an analytic side that I have to deal with, I want to be able to go a little bit further. Well, what are we really talking about? In this region where I'm saying f prime is increasing, that the f is concave up, well, what would I do if I wanted to figure out, well, when is f prime increasing? Well, f prime would be increasing when the derivative of f prime is positive. Well, the derivative of f prime is f double prime. So now we're going to introduce a new function. We're introducing an f double prime function, which is the rate of change of the rate of change of f. It's a second derivative. And when I look at this rate at which f prime is changing here, you'll notice that during this whole section that is increasing, f double prime is positive. If I go back, I'll use this one. In this whole region where f prime is decreasing and my function is concave down, you'll notice that f double prime is always negative. And those are the relationships that we are going to use today. Specifically, we're going to come up with a definition of concavity that states that a graph of f is concave upward on an interval I if f prime is increasing on the interval. Or the graph of f is concave down on the interval I if f prime is decreasing. Now, one thing I do want to point out, you will notice that concavity is defined on an interval I. Concavity is not going to happen at a specific point, unlike increasing and decreasing, where we might say at this point this is an increasing function. They are very, very asinine about that, making sure that you understand concavity is over an interval. So if I ever ask about the concavity of something, we are always going to state that the concavity is positive over an interval containing a point, and we're going to see an example of that momentarily. Our test for concavity, now our definition is talking about f prime increasing and decreasing. Our test exists because we want to come up with something that we can do easily without having to graph functions to be able to observe whether f prime is increasing or decreasing. So the way we're going to test for this is if we have some f in which a second derivative, so for those of you who have noticed maybe a couple questions that say a twice differentiable function, hopefully you're recognizing, oh, now we're saying that we can also find concavity. Then if that second derivative is positive for all x on the I, then the graph of f is concave up. Or if f double prime is smaller than 0, negative, we say that the graph is concave down. And by the way, usually we call this CC down, and I'll say CC up for concavity. So if my idea of concavity is based on f double prime being negative or positive, then we can come up with a definition for an inflection point. We can say that a function f has an inflection point, CF of C, if we're going to specifically find the spot where f double prime of x is 0, or where f double prime of x does not exist, because those two things could occur. That will cause an inflection change. But if f double prime is 0 or does not exist, and f double prime changes sign from positive to negative, or negative to positive at C, or if f prime changes from increasing to decreasing, or decreasing to increasing. Because our definition of an inflection point is a point where concavity changes. So real quick, let's just, looking at the first example, we were given a graph. I want to state what is the sign of f prime and f double prime on the interval from 0 to 3. We would state f prime. I would suggest pausing this, trying to write it down, come up with a solution for yourself first. I'll give a second for that. try to think about what you think f prime will be and what f double prime will be. If you haven't paused the video, you might not have had enough time, but if f prime is talking about whether the function, oops, I want to mention one thing. This is the f graph here. So this is the graph of f, and we're talking about f prime and f double prime. If we're talking about the f function, we can see the f function is decreasing. It's moving down. That means that the f prime graph, oops, I don't know why I put an equal sign, is negative since f is decreasing. F double prime, then, if I take a look at that, I want to deal with the concavity. If I notice, this is kind of looks a lot like this piece right here at least, and it doesn't look like it ever changes. Looks kind of like an upward facing parabola. We can say that f double prime is positive here since f is concave up. We're going to be very picky about f prime, f double prime, making sure that we're using those names of the functions correctly. I'm going to be very explicit with that, or not explicit, but be very particular about that and hold you to that standard, because if you can keep that straight in your words, you'll keep it straight when you get to your knowledge, really solidifying what we know. So for the following function, we want to do the following. We want to find intervals where f is increasing and decreasing, the local maximums and the local minimums, and now an interval of concavity. So now we got to do a bunch of stuff. So the first two are nothing crazy. How do we find increasing and decreasing? You take the first derivative, you say that's 4x cubed minus 12x squared. We find the critical values. There's no spot where this will be undefined. I can factor out a 4x squared, which leaves me with x minus 3. We set that equal to 0. We find out that we have critical numbers at x equals 0 and 3. So when we go and evaluate this, if I pick some really crazy, just any negative number, that's a positive times a negative, which is a negative. When I jump over the 0, that's an x squared, doesn't change sign, so that stays negative. And then we say that there is a positive at x equals 3 because there's a sign change there. And we can make our statements about increasing, decreasing, and max and min. This increases, f increases on 3 to infinity, since f prime is greater than 0. And we can say that f decreases on negative infinity to 0 and 0 to 3, since f prime is less than 0. We also asked to make a statement about relative extrema. There's only one spot where there's a sign change here, and that is a relative min at x equals 3, since f prime changes from negative to positive. So this is all the stuff that we've done before. Here's your A stuff, increasing and decreasing. Here's your B stuff, relative min. Now we got to add on the concavity and inflection points. So to do a concavity question, we need to come up with a second derivative. F double prime. You've got your choices. You can take the derivative of either 4x cubed minus 12x squared or 4x squared times x minus 3. I don't like the product rule, so I'm going to choose to take the derivative of 12x squared to 12x squared minus 24x. And again, just like I did before, I'm going to come up with when f double prime equals 0. Now, point of order here, these are not critical points. All right? The points that I find here, when I evaluate 12x and I get x minus 2, and I set this equal to 0, and I get x equals 0 and 2, these are not critical numbers. Okay? They're just possible points of inflection, what we call them. We call these possible points of inflection. It gets to be a bit annoying, but we want to save the word critical number for the concept of extrema. because when we're dealing with extrema, that's typically what we're interested in real-world applications. Points of inflection, they can be important. We're going to see an example much further down the road where those are important, but in application. But right now, there's not much we can do with these. So I got my 0, I got my 2. I create my chart, 0 and 2. It's a positive quadratic, plus minus plus. Always fun when we can do that. We say that f is concave up on negative infinity to 0 and 2 to infinity, since f double prime is greater than 0. And we say f is concave down on 0 to 2, since f double prime is less than 0. We also say there is a point of inflection, which I will, after writing it once, I will now abbreviate as POI. We have a point of inflection at x equals 0. And now here's where things get fun. The straightforward way to write this is that x equals 0 since f double prime changes from positive to negative, and at x equals 2 since f double prime changes from negative to positive. I'm going to show you the way that I write it, which is correct. It cheats a little bit. You still only work on concavity. It does not work on critical points. So if you want to have the same thing, write it as two separate statements. I'm going to write it as a single statement. At x equals 0 and 2, since, and what I say is I say, since f double prime changes between positive and negative. And the importance here is that if I say changes between the positive and the negative, I'm allowing this to change both between positive and negative and positive. I'm saying there's just a sign change. If I say from is specifically giving me a directional thing from left to right, and I have to make that statement. So again, if I wanted this to be correct in a full statement, it would have been point of inflection at x equals 0 since f double prime changes from positive to negative, and at x equals 2 since f double prime changes from negative to positive. Your choice how you want to say that. All right. Again, following the same concept, I'm going to skip over this one. I want to move down. We'll look at that one in just a minute. I want to look at 3 and 4, and then if I get a chance, I'll come back up to that one. So number 3. The graph of the derivative f prime of a continuous function f is shown on what intervals is f increasing or decreasing? So first off, what are we looking at? This is f prime. Okay, so I've got to justify anyways. So I know f increases when f prime is positive. Look, I've justified my answer. So what region is that? That is -3 to 1 and 4 to infinity. F decreases when f prime is negative. And again, I want to just point out, I'm not saying the function increases, the function decreases. I'm saying f, because f prime is a function, and f double prime will be a function, and f is a function. What function is it? So f prime is negative on negative infinity to -3 and 1 to 4. I probably should have let you do that beforehand. Oh well. So now let's take a look at B. At what x values of f does f have a local maximum or a local minimum? Justify. I will give you a moment to pause the video to try this out. Write it down. Hopefully you paused the video there. So after you've taken the chance to pause and you've tried this out, we would say f has a local max when f prime changes from positive to negative. Where does that happen? That would happen at x is equal to 1. F has a local min when f prime changes from negative to positive. That occurs at x equals -3 and 4. finally see on what interval is f concave up or concave down. We know that f is concave up when, now there's no f double prime. So this is going to be important. F is concave up when f prime increases. Notice I didn't say f double prime. Unless you plan on actually showing me what f double prime is. If you plan on graphing f double prime, you cannot defend with f double prime. You have to defend with f prime. So this is where things get weird. So where does f prime increase? It's going to increase from negative infinity to negative 1. So if you have the opportunity, I'm going to give you a second to pause and decide if there's any other spots where this is going to increase, where there's going to be a concave up section. Hopefully you paused the video there and you found a second region. The second region that we would be finding would be 2 to infinity. We're also looking for f is concave down. So this time again we're going to defend with when f prime decreases. And that is the intermediate section of negative 1 to 2. So what we want to do is we want to be able to graph things. We want to be able to look at some of these things. So if I want to sketch a function, this is always good practice, gets us thinking. I'm going to let you go ahead and pause and play with the sketch and see if you can come up with one. All right, so hopefully you've managed to pause and tried to make a sketch. Things I'm looking for, I know that when the x is 0, when the x is 2, they both equal 0. So boom, there's a 1, there's a 2, check. Do the next piece in the next color. The next one says f prime of x is positive if x is less than 1. So what does that mean? It means f increases on, in this case, x is less than 1. So I know I need to go up for some reason here. I tell you f prime of 1 is equal to 0. That means that there is a critical number at x is equal to 1. And I tell you f prime is negative when afterwards, so I know that f decreases on x is greater than 1. These three things are the first derivative test, meaning that x equals 1 is a relative maximum. The next thing I know is that f double prime being negative means that f is concave down. So I need something that is concave down, that increases to here and then decreases. You're done. By the way, concavity doesn't exist on like absolute value functions. It's because those are linear. There's no curvature. So concavity is dealing with curvature specifically. I will also give you a second to pause to answer the very last question. All right, so for which of the following values x is f prime positive and increasing? So this is my graph of f. F prime is positive means x is increasing. So what letters can I omit? I can omit A. I can omit B. I cannot omit C, and I can omit D. So the answer better be C or E. F double prime is, or F prime is increasing means F is concave up. This region is concave down. This because it looks like a downward facing parabola. This region right here looks like an upward facing parabola. Your answer is E. At this point in time, you've gotten everything that you really need from this section. It's already been 25 minutes, so I don't want to go too long. For those of you who would like to see the first question up here, I'm going to go ahead and take the opportunity. So for those of you who who think they can figure that out, awesome. If you want to figure it out first and then try to watch the video on it later, that's fine as well. So I'm going to go ahead and take care of that. So this says f of x is equal to 3x. This is the same thing. Find f is increasing, decreasing, local max, min, and concavity. So the step one, let's do f prime of x. This is a chain rule. So this is 3e to the x plus 3x e to the x. So when I factor this out, I can factor out a 3e to the x times 1 plus x. Set that equal to 0. The only critical number is x equals -1. So if I'm looking at my f prime graph at -1, our function will be negative on the left and positive on the right. So we say f increases on -1 to infinity. Since f prime is greater than 0, we say f decreases on -infinity to -1, since f prime is less than 0, and that we have a relative min at x equals -1. F prime changes from negative to positive. Nothing crazy. That's the A and B stuff. That's what we've been practicing the last 3 days. Concavity jumps in. I've got to take a derivative. So now I've got f double prime of x. I've got options. I can take the derivative of 3e to the x plus 1 plus x. I'm going to take the derivative of 3e to the x plus 3x e to the x. Derivative of 3e to the x is easy. That's 3e to the x. Plus the derivative of 3x e to the x is actually pretty easy as well, because we literally just did that. That is 3e to the x plus 3x e to the x. I'm just going to copy. This is kind of weird. It's the self-replicating derivative. I've got some like terms. We can call that 6e to the x plus 3x e to the x. I apologize. It's late right now. I'm currently making this video at 8:30. Ay, ay, ay. I'm going to factor out a 3e to the x to leave me with 2 plus x. Again, my possible point of inflection is at x equals -2. This is now my f double prime graph. Notice I'm trying to label these so that you can make sense of which sign chart I'm dealing with. So my values are going to get plugged back into here. This will be a negative and a positive. So we know that f is concave up on -2 to infinity. Since f double prime is greater than 0, we say f is concave down on -infinity to -2, since f double prime is less than 0. And finally, we want the points of inflection. So we say there's a point of inflection, f's point of inflection at x equals -2, since f double prime changes. And this time it doesn't really matter. I'm still going to use between when I talk about points of inflections. I like to be consistent between negative and positive. Those of you who watched till the very end, there you have it. There are the concavity notes. There are questions inside of your unit tracker to have you try out these questions. Tomorrow, hopefully I will be here. If I am not, I will have come up to the school to make the next video for what's called the second derivative test. And when we get to that, we will have an opportunity to discuss those and try to get together. There will be a test at some point in time next week, and I'm playing with the idea of having the test possibly during class. It's a relatively short test, and I want to make sure to get that in and graded before you get the CBA, so that on the CBA you have the ability to do well on that. My promise to you on that will be is if you don't like your grade from that second test, if we do it in class, that you will be able to wipe it out with the CBA grade. So that's it for me. That is hopefully useful, and I look forward to seeing you as soon as I have the opportunity. Thank you very much.